we're now at the point in the course where we're going to start to apply special relativity to electrodynamics, how the electric and magnetic fields are used in special relativity, which should be a natural transition because most of what we've done in the second half of this course is talk about light, which is just an oscillating electric and magnetic fields, and light. The speed of light is the constant in all frames of reference, and so therefore we should be able to start looking at how light behaves given different frames of reference. So we're going to start with an example in magnetism, and this may take a couple of videos to actually go through the whole topic, but I'm going to start with this example where we have basically two lines of charge. A negative one, which is moving to the left at minus v, a positive line, which is moving to the right with a positive velocity. The line density is minus lambda for the negative charge. Positive lambda is the line density for the positive charges. And we're going to have a point charge q, which now is moving to the right with a velocity u. And it's at some distance s away from these lines of charge. So if I wanted to see what the current of the lines of charge were, the current would be 2 times lambda times the velocity. So that's the total current in the system. And from the point charge q, from its point of view, if we have equal amounts of line density, so if the magnitude of the positive and negative line charge densities is equal to each other, then there is no force. So no electric force on Q. Okay. So let's look a little bit deeper at this. So this, I'm going to say, is this situation is going to be frame S. So frame S, it has basically declared itself to be at rest with all of these charges moving relative to frame S. Now I could put myself in a different frame. So I could now be, let's say, in a frame S bar, where this person now is moving with a velocity u relative to frame S. When it does that, if frame S bar matches velocity with the point charge q, so from their perspective, from the perspective of S bar, then Q is at rest. It's not moving, because if Q moves a meter, then and the frame moves a meter, then their observations are that point charge Q is not moving. But then we can say, well, what is the observation of frame S bar of the lines of charge? Because they're moving at different velocities with respect to the point charge. So what we can do is we can look at now the velocity measured by S bar. So the velocity plus and minus. So the plus is for the positive line charge, minus is for the negative line charge. So our relativistic equation then for those velocities is the velocity measured by S minus plus the velocity of the frame, u, divided by the factor 1 minus plus vu divided by c squared. Okay, so that's the velocity measured by S bar of the line charges. Okay, so let's take a look at the actual charges themselves. So what we could say is lambda plus minus is the charge densities measured by frame S bar, and that would be plus minus a gamma factor measured by or applied by S bar times lambda naught, where lambda naught is now the charge density if it was at rest. So if you were one of those charges, you're one of the positive charges in the line density, from your perspective, all your other neighbor charges in this line density are not moving, and so you would measure the charge density to be lambda naught. Okay, so now the gamma factor, this gamma plus minus, would just be the usual gamma factor, 1 minus the velocity plus minus divided by c quantity squared. So we have to figure out what is that gamma plus, the v plus minus. Well, it's given above right here. So you'd basically have to put that in to this equation to get the gamma factor, to get what the transformed line charge is going to be. Now, from the perspective of, this follows the same from the perspective of, say, frame S. So from frame S's perspective, the gamma factor is 1 over the square root of 1 minus v squared, v divided by c quantity squared. And you can then measure the line charge lambda in the frame S as gamma lambda naught. So, so for each of the frames, either frame S or S bar, we have these gamma factors. Okay, so let's work out the gamma factor for the S bar frame. So we'll go back to frame S bar, and we'll start with this gamma plus minus 1 over 1 minus the velocity term times 1 over c squared. And this whole thing, we take the square root. Okay, so now what we can do is, well, I can now factor out the c squared. Oh, I'm sorry, this term is squared. So that parentheses is squared because the velocity squared divided by c squared. So we can factor out the c squared, and what we should get is 1 over 1 minus 1 over c squared times c to the fourth of v minus plus u over c squared minus vu quantity squared. All of that we take the square root. Okay, so let's clean this up a little bit more. This gives me a c squared, and now what I want to do is take the denominator and bring it out. And so I would get a c squared minus plus c squared minus plus vu in the numerator, c squared minus plus vu minus c squared v minus plus u quantity squared, and then all of that you apply a square root to. Okay, so now we're just going to, and then, sorry, this is a squared. I make sure to don't forget the squareds. Okay, so let's multiply out those quadratics. We would get c squared minus plus vu over c to the fourth minus plus 2vu c squared plus v squared u squared minus c squared times v squared plus minus 2vu c squared plus u squared, and then all of that to the square root. We can start canceling some terms, And in the end, what we get is c squared minus plus vu divided by c to the fourth plus v squared u squared minus c squared v squared, that's a c squared in there, plus c squared, be careful, so that's a minus c squared u squared, and then I get a minus c squared u squared, all of that to the square root. Okay. So it turns out that this denominator you can factor, and so what you get is c squared minus v squared quantity c squared minus u squared, all of that is taken to the square root. Okay, so now if I divide the numerator and denominator by c squared, I would get 1 minus plus v times u divided by c squared over the square root of 1 minus v squared over c squared, square root 1 minus u squared over c squared, like so. And if I look at that, this is just gamma from the frame of, from the S frame. And so in the end, what I would get is a gamma times 1 minus plus vu over c squared divided by the square root of 1 minus u over c quantity squared, like so. Okay. So in the end, now we have the gamma factors. If you remember, this whole thing was gamma plus minus. So now that we have those gamma factors, we can now take a look at, in the frame of S bar, the net charge from those two lines of charge are the charge from the positive and the charge from the negative. And if I put that in, I get the rest charge times gamma plus minus gamma minus. Or if you put in those gamma factors, what you get is minus 2 lambda v times u over c squared 1 minus u squared over c squared. So this is now the net charge that you would have, which is interesting now because we now have a net charge. And if we have a net charge from the line densities, then we would have an electric force. So, so the last word I'll say about this is the fact that where do we get these net charge densities? Well, we get them because there is a contraction. There is a length contraction, which causes an uneven grouping of the charges. So instead, so what you would get is essentially a bunching up of the positives and negatives in the what you would get is a bunching of the positives and negatives. So in the end, what you would have is a contraction of all these charges kind of grouped together now. And since what we have is, this is our person now moving with a relative velocity u. And so from our perspective, you've changed the length. And since these are line densities, you've changed the actual form of the density. Okay, so in the next video, what we'll do is we'll take a look at what's the electric force that's going to be applied, because now that we have a net charge density.